Okay, well, as you see, today we're going to start recording these lectures, and the reason is because we have, we're using the 5th edition. And so up until now, with the chapter on combinational circuits and the chapter on sequential circuits, that material is virtually unchanged between the 4th edition and the 5th edition. But in chapter 12, it's considerably changed, and I want us to use the latest, greatest material for this. Now, there's going to be a slight difference here in that up until now in this course, we have always been talking about working our way up to actually constructing the PEP-8 CPU. But here's the thing, with the 5th edition, it's not PEP-8 anymore, it's now what? PEP-9. So the CPU is just slightly different from the computer, the organization of the CPU is just slightly different. And also, the instruction set of PEP-9 is a little bit different from the instruction set of PEP-8. Okay, so the mnemonics are a little bit different, and I'll point those differences out as we go on. But you'll see it's very, very similar. I think switching from PEP-8 to PEP-9 midstream in this computer organization course is not going to matter. It'll be pretty painless, I think. All right. So with that in mind, we're going to start with computer organization. Now, the word computer organization in computer science or in computer systems means the organization of the CPU. Okay? And on this slide, what we're doing, what is shown on this slide is that we're moving from the logic gate level down here, which is where we did the combinational circuits and the sequential circuits, and now we're going to move up one level to the microcode level. So now that's the level between the ISA level and the logic gate level. So now is where we meet. So this is the grand finale, you guys. You guys, in computer systems, we went down, and here we started down, and now we're going up, and now the twain shall meet. East meets west. North meets south. Instruction set architecture level meets logic gate level. Okay, so now we have a meeting of the minds, and so that's the 7 levels of abstraction in a typical system, and we are now at MIC 2, microcode level 2. Actually, previews of coming attractions. It's actually possible to design a computer system without MIC level 2. And we are also going to investigate that possibility later on in the course. Okay, so now let's take a look. Up until now, when we talked about, or when we described the central processing unit, we always considered that it was just a single block, right? And do you remember some of the things that are in the CPU? What are some of the things in the CPU? Some registers. Yeah, you're right. But which registers? Do you remember some of these specific registers that were in there? Instruction register, index register. The opcode is part of an instruction, okay, but instructions are stored in the instruction register, so the opcode is part of that. So you could say that's part of it. What else? What other registers? NZVC bits, yeah. Accumulator, index register for, yeah. PC, program counter, yeah, all that. Now, all of that stuff that we talked about being in the CPU, all of that is in the data section. We have only showed you the data section. But now what we're going to see is that the CPU is divided into 2 sections, a data section and a control section. Are you with me? And the control section has been invisible to us at the ISA 3 level. So the data section receives data from and sends data to the main memory subsystem and the input-output devices. And it's the control section that issues the signals to make stuff happen in the registers, makes the computation happen in, using the registers in the CPU. So here is a picture of the PEP9, of a typical PEP9 system. Now also, you guys, this is a little bit different from the model that we used for PEP8. Notice, do you remember the model that we used for PEP8 when we had the bus? What's along the bottom? What is a bus? What is the bus? What is a bus?
Wires.
It's a bunch of wires. So, we had the bus. Do you remember what we had in the PEP8 model? What the 4 blocks were? Do you remember what they were? We had the CPU and we had main memory, but then we had what? Yeah, well, we had an input device and an output device. Remember that? Well, I've changed the model. We've changed the model a little bit. Now what we've got is disk, because disk is both input and output, and every computer system has a disk hard drive, either solid state or mechanical. All right. So now we're showing the model a little bit differently here. But now the main. Oh, one more difference between PEP8 and PEP9. Notice here that in figure 12.1, main memory has an input port and an output port. Now what this means is that in the PEP9 system, there is no character input or character output. Do you remember these in PEP8? So you remember these? Carry and caro. So that would input and output a single character. Well, there is no carry caro in PEP9. Because in PEP9, it uses a system that's more common in the real world. It's memory mapped I/O. So the input port is at a particular address in main memory, and the output port is at another particular address in main memory. So instead of doing a carry, guess what you do? You do load accumulator. Well, the mnemonics are a little bit different too. So this is PEP8. This is PEP9. Instead of doing carry in PEP8, what we do is load accumulator, load word accumulator. This is, now the mnemonic is a little bit different. So instead of load accumulator, it's load word accumulator from the input port, which has a symbol char in using direct addressing. And what that does is that gets the input into the CPU. Do you see how that works? And then instead of doing char-o, it's, what do you suppose it is? If you do load word from the input port to get a character into the accumulator, how do you send it from the accumulator to? Yes, store. And it's, instead of STA, like it was in PEP8, in PEP9 the mnemonic is store word accumulator, and this is to char out direct. Okay, so these are two differences between PEP8 and PEP9. But we're not going to deal with programs up at that level, so this is not going to really concern us very much, because we're going to be more interested in how the CPU itself is organized. Okay, but now here, check this out. The CPU itself is divided into two sections, the data section and the control section. Are you with me? So here we go. And now what we're going to do today is we're going to find out how the control section controls the data section. All right, now this is going to be a kind of a complicated picture, but here it is, figure 12.2. Look at this son of a gun. It looks like it's really, really big. It is really, really big, well, by our standards. But let's just break it down into all the specific parts. It looks real complicated, but it's not. We can get this. Let's start at the top. I actually have a expanded version here on the slides. Figure 12.2 expanded shows the top part of that figure. Now, does that big block at the top look familiar? Remember, we showed how that is designed. I think, was it just last time? Yeah. So that is that register bank. And here we have, so how many inputs? Can you count how many inputs it has? Well, if you, individual lines, how many individual lines do you suppose it has? Input lines, how many individual input lines? Let me see. More than that. Good question. How big is the bus? The bus is 8 bits. So all those fat arrows are 8-bit. In other words, 1 byte. You counted how many? 24. Well, there's 5, 10, 15 for ABC. 16 plus 8 for the C. You're right. 24. Everybody clear on that? And how many outputs? 16. 8 data bus, 8 for the A bus, and 8 for the B bus. Okay? And so let's just go down. The next component in the CPU is the MARA and MARB. Okay? So MAR stands for Memory Address Register. Okay? So Memory Address Register. That's the MAR. And how many MARs do we have here? How many little MAR blocks do you see over there? 2. There's 2 of them. There's an MARA and an MARB. So MARA is the high order byte and MARB is the low order byte. Now, how big is an address in PEP 9, PEP 8 or PEP 9? You know, whenever we would do an address, do you remember how many address lines? Here, whenever we did load, if we do load word accumulator 0x00AB direct addressing. How many addressing lines did we, how many, you know, whenever we would say load from this, direct addressing from this address? Well, how many? 16, yeah, 16 bits. Okay, so that MARA and MARB together make up 16 bits. The MARA is the high order 8 bits and the MARB is the low order 8 bits. Is everybody clear on that? So that, and notice that it's pointing to the system bus, right? So look, let's go to the regular figure. So you see, look, that goes to the system bus. Now, do you see that there's 2 parts to the system bus? The system bus has address lines and it has data lines. Are you with me? Over here. My pointer doesn't work. But up here, right? So you see MARA is going to the system bus. MARA and MARB are both going to the system bus. So that system bus is 16 bits wide. And furthermore, the information comes, how does the information get into the MARA and MARB? Can you tell just by looking at the plumbing there?
From the A and B bus?
Yeah, from the A bus and the B bus. But then the A bus and the B bus come from where? From that register bank up at the top. Are you with me? Is everybody clear on that? So do you see what we're going to do is all this is plumbing, and these are pipes. And all we're doing is we're using multiplexers to switch where the information goes. You see how, you see? So information can go from the A bus and the B bus into the MARA and the MARB. All right, let's go. So on this slide we have the CPU components. So we've talked about, we have a 16-bit memory address register, MAR, and that's divided into two registers, an 8-bit MARA and an 8-bit MARB. Now the next thing that it has is a memory data register, MDR, which is 8 bits. Okay? So let's take a look at that. So you see do you see the box labeled MDR? It's right over here. Okay? So that's the memory data register. Now, here's the thing. The memory data register is in between the CPU and main memory. So do you see where main memory is? It's down there on the lower left. Are you with me? And so what can happen is data can come from the main memory up over the data bus and into the what? What is this? The MDR MUX multiplexer, and from that it can get into the memory data register. Are you with me? And then another way to get information, what's another way to get information into the memory data register? Yes, you see there's a path from the CMUX through the MDR MUX into the MDR. So you see there's two ways to get information into the memory data register. Either from the MDR MUX, it always comes from the MDR MUX, but it can either come from the system bus or it can come from CMUX. You see how this is just plumbing and we just visualize water flowing through the pipes. Okay, so that's the MDR. And now we have a set of multiplexers, 8-bit multiplexers. We've got AMUX, CMUX, MDR MUX, and each one of these MUXes, each one of these multiplexers is 8 bits. So really what it is it's a bank of 8 two-input multiplexers. Do you see what I mean? It's a bank, each one of those is a bank of 8 two-input multiplexers. Are you with me on this? So here, let's look at where they are. The AMUX, the CMUX, and the MDR MUX. So let me see, where's the AMUX? It's right here, yeah? Are you with me? There's the AMUX. And it has two things coming in from the top, two inputs from the top and one output on the bottom. And then what about that single line coming in from the right? What is that? How's that labeled? That's the label of that. That's a control line. This little AMUX coming in from the right. That's a what is its label? Yeah, that is an AMUX. So it has the same name as the multiplexer, but it's a control line. And here's how that works. The way that works is, and this is going to be our convention. The way that works is 0 on a control line means left, and 1 on a control line means right. So let's visualize how that works. So here's the expanded view. So you see AMUX is coming in from the right. And that is a control signal. And when that is 0, what is the output of the AMUX? Tell me, just by looking at the figure, if this AMUX control line is 0, what is coming out of the AMUX? MDR. Yes. The MDR is going through. And if that AMUX is 1, what is coming through the bottom of the AMUX? The A bus. Are you with me? So that's always going to be our convention. 0 left, 1 right. Are you with me? Now, actually I should have said this at the beginning, but here in this complete figure 12.2, what we are seeing is the data section. Now, do you see all these arrows coming in from the right? All those arrows coming in from the right are where are they coming from? What is not shown but is to the right here? The what? That is the control section. Are you with me? So if we come back to this picture here, see the data section is on the left, the control section is on the right. And so that is hidden for the time being. The control section is hidden for the time being. We don't know exactly how that works, but what we do know is that those control signals are coming in from the right. Yeah, question?
So the control...
Oh, that's a really good question. Here, figure 12.1, this dashed line that is going from the control section to this bus, let me show you where those are. Those, you see here at the very bottom, this memwrite and memread, that's those. Because look, where do they go? To the what? To the bus. Now, those other ones are actually, the ones that are coming from the left here, those are actually inside the control section and going to the data section. So they're not shown on figure 12.1.
So the data section and control section are pretty integrated?
Yes, they are very integrated. They are right next to each other. Yeah. Yes, they are. Yes. Yeah. Is everybody clear on how this is on the organized? It was a good question. Is everybody clear on how that's organized? Yeah. So this dashed line, because this line is a line that's coming from the control section to the system bus. This line along the bottom is the system bus. So there's 3 kinds of wires on the system bus. There's address lines, data lines, and control lines. That was a good, nice observation. But everything over here on the right is the control section. And what it does, why is it called the control section? Because it controls how the data flows in the data section. See? Are we good? Is everybody good so far? So we just talked about the AMUX. Now, what other muxes do we have? What other 8-bit muxes do we have on this figure? Yeah, CMUX, so let's think about that. So the CMUX is just to the left of the ALU, right? Correct? And you see there's a CMUX control line that goes in there, and if that CMUX control line is 0, what goes out the top of the CMUX? Holy moly, what in the world is all that stuff? Oh! What else do you see here that somebody said was in the CPU?
Status bits.
The status bits. Notice that the status bits are not up in the register bank. They're down here. Now, do you recognize, which ones do you recognize here? Which status bits do you recognize here? Yeah, it was NZVC. But now what else do we have? S. This is new in PEP 9. S is the shadow carry. We'll talk about that in a minute. But here what we have is NZVC. And you see that NZVC all go to the, where do they, the outputs of those NZVC all go over here to what? To the least significant nibble. You guys know what a nibble is? We talked about this, right? A nibble is 4 bits, NYBBLE, half a byte. Half a byte is a nibble. So those 4 NZVC bits go to the least significant, and then zeros go to the most significant nibble, and those together, those 8 go up to the left input of the CMUX. Are you with me? And then so that's what comes out to the top of the CMUX, yeah? Now, so we look, oh, and if CMUX, by the way, if CMUX is 1, then what shoots up out the top of the CMUX? If the CMUX control line is 1. The ALU, and do you remember what we called that? There's not enough room to label everything here, but do you remember what we called that output of the ALU when we designed the ALU? Do you remember what we called it? I think we called it result, didn't we? You don't remember? Too long ago? Yeah, you guys actually did. You designed part of the CPU, but anyway, I think we called it, I think if you look back in the figures there, you call it result. Oh, and well, you do remember that we had A and B for the input and result on the output. So the A and the B corresponds to the A bus and the B bus. Notice that the A bus is, well, it has to go through the A mux to get to the A input of the CPU, of the ALU rather, right? Okay, so now so we looked at the MDR mux and the A mux and the C mux. Is that? Yeah, those are the 3 8-bit multiplexers. Now there's another mux. CS mux. But now, can you tell from the CS mux, can you tell how many, is it like an 8-bit wide path?
So we got 2 1-bit, or 3, excuse me.
Well, the CS mux is the control line.
Oh, yeah, never mind, so it's just 2.
So yeah, so what do you suppose? If the CS mux control line is 0, what goes out through the top?
C.
The C bit. And the C bit will go into what? That will be the what of the ALU? The carry in. Are you with me? But we can also choose to have what happen? If CS mux is 1, then what? The shadow carry is the C in to the ALU. Do you see what I mean? So we can pick what is the carry in to the ALU. Are you with me, sports fans? Okay? And furthermore, the C out of the ALU, where does that go? It goes to the shadow and the carry. It taps off there. Right. Here, we can do a close-up of that. Notice that the C out here goes to both the shadow and the carry. So which one is it going to get clocked into? Well, what's another control line there for the S bit and the C bit? What is this? What do you suppose this line is? SCK, that's a clock pulse. If we choose to clock it, then the C out will go into S. If we choose to clock this one, C out will go into C. So we could do it to either or both, or neither, on a particular cycle. Are we good? Okay, so we've just about finished. So we did the muxes. Let's take a look at this slide, the control signals. The control signals originate from the control section on the right, not shown in figure 12.2, and there's 2 kinds of control signals. The clock signals end in CK to load data into the registers with a clock pulse, and the signals that do not end in CK are the signals to route the data and present it to the sequential circuits so that when a clock pulse happens, boom, that data will be clocked into that sequential circuit. Is everybody with me on this? Are we good? So here is some more information on stuff that we have gone over. The status bits, NZVC. Each status bit is a 1-bit D flip-flop. And so you know how D flip-flops work? It just copies the data into whatever the input is, that's what That's what goes into the D flip-flop. And each status bit is available to the control section, and the status bits can be sent as the low order nibble to the left input of CMUX and from there to the register bank. So we saw that. Yeah? And then here is the shadow carry. Now, we explained how the shadow carry worked in the organization, but why do we have it? The shadow carry bit, now what is abstraction? Hiding of detail. So the shadow carry is invisible at level ISA 3, but it's visible at level MIC 2. And now here comes the big numero uno question that everybody has tattooed, we all have tattooed on our foreheads. What's the von Neumann cycle? Fetch, decode, increment, execute, repeat. So now, when you increment, what are you incrementing? The program counter. Because the program counter stores what? The address of the next instruction to execute. So when we add, but now look, how are we going to add? How many bits is the program counter? Let's go back to our register bank. How many bits is the program counter is down there on the lower left corner of the register bank? It's 16 bits. But how big is the A bus and the B bus? They're each 8 bits. So how are we going to increment the program counter by 1? We're going to have to do what? Do them one at a time. Which one should we do first, the high order byte or the low order byte? We're going to have to do the low order because then it'll carry over into the high order. We have to do that first and then store the carryover to the high order. So now, when we add 1 to the program counter, we'll have to add the low order byte of the program counter to, now is there a 1 up here? Is there a constant 1 in this register bank?
23.
Yes, number 23 is 1. Does everybody see that? That's a read-only memory 1. So to add 1 to the program counter, we'll take that 1. We'll take the program counter, the least significant byte, which is register 7 in the bank, and 23, which is the 1, and we'll add them. And then what will we have to do? We'll have to save the carry in that cycle so that we can do what? Add the carry, any possible carry, on the second cycle to do the high order byte. Does everybody see how that works? And if there's a carry in that intermediate one, we don't want to change the carry bit for the user at level ISA 3. So that enables us to do a 2-byte add as 2 1-byte adds without messing with the carry bit that's visible at level ISA 3. Does everybody see the idea there? So let's go back and read this again. Yes, it's used for internal arithmetic operations that should not affect the C bit. The example we have here is PC gets PC plus 1. And it's selected by CSMUX equals 1. And next is how we set the status bits. So now this is a little tricky, especially with the Z bit. So let's take a look at C and N and V and Z. First of all, let's take a look at C. Let's take a look at where C fits in this organization. So let's go to this expanded view at the bottom. And here the C bit can be stored from the C out of the ALU, and it can also be used as the C in of the ALU if it goes through the CMUX. If the CMUX control line is 0. Are you with me? So do you see how it's both output and input? The C bit is both output and input to the ALU. The S bit can also be both output and input to the ALU. So does everybody see how the carry bit works? See? And what does V stand for? What does V use for, the V bit? Overflow. That's signed integer overflow. And V can be set from where? Where does V get its data from? The what? Well, yes, but that computation of the carry and the penultimate one, that's all done inside the ALU. But outside the ALU, how can V get set? It's one of the output lines from the ALU. There's a V output from the ALU, if you go back and look at that. All right, and it can be clocked in with the VCK. And then it can also go to that rightmost nibble, one of the bits of the rightmost nibble. And do you see that N is the same way? The N bit can be clocked in from the ALU, and it is also part of that right nibble that goes through the left input of the CMUX. But now here's a little complicating factor. What about this Z? Now do you remember here? Do you guys remember this? How did this... N, remember N is negative. That's just a copy of the sign bit, right? Z was what? 0. But now, so this is copy of. So N was copy of the sign bit 0, and V is overflow, and C was carry. But when is Z 1? When what? What makes, remember when we would do those exercises and we'd say, now what is the value, I was doing an operation and we'd say, what's the value of N, Z, V, and C? Do you remember how you determined what Z was? Z is 1 if they are all zeros. All how many? All how many are 0? If we did an add, suppose we did add accumulator. Suppose we did add accumulator. How would we determine if Z was 0 or 1? All 16. 0. So it's 1 if all 16 bits are zeros. Are you with me? Is everybody clear on that? Sure.
Isn't the result 8 bits?
Yeah, yes, the result is 8 bits. A bus is 8 bits, B bus is 8 bits, and result is 8 bits. But as far as the user at level ISA3 is concerned, how big is the accumulator? It's 16 bits. Are you with me? And when we did those calculations of how to calculate Z, what did we look at? All 16 bits had to be 0 in order for the Z bit to be 1. Now this is really important. Is everybody clear on how we did that? Remember how we did that? Okay, so now look. On the other hand, we can only do, because our internal data buses are only 8 bits, every 16-bit operation has to be done how?
Split it.
You have to split it in half. You have to do a low order and you have to do a high order. Are you with me? Because at level ISA 3, it's 16 bits. But here we only have 8. So we have to do it in half. You have to do the one half and then the other half. So how in the heck are we going to determine if all 16 bits are 0? If we do a lower half and an upper half. If we do a low order and then a high order. How are we going to how will we do that? Can you see by this circuitry how we will do that? Just kind of, I mean, we haven't actually done an example of a cycle yet, but can you see how this is going to happen? How is this going to happen?
We probably do it, and then that and Z, we have to say, oh, this was the lower half Z, because we can only determine if the entire 16 bits are Z after we've done the high order.
Yes, so that's exactly right. So tell me, what will we do on the low half? What do we want to do when we have the result of the low half? What will we store inside of Z?
Just the value of the low.
Just the value of this Z out. Are you with me? So we will want just the value of the Z out to go through this and to be clocked into this Z bit. Are you with me? But then on the high order half, what will we want to be clocked into this Z bit? What has to be true?
The and that Z out and the previous Z out.
Yes. If the high order 8 bits is also 0, then the Z out of the ALU needs to be what? ANDed with this, because you could have 0 in the low but not in the high. You could have 0 in the high but not in the low. But when you want it to be set is when you have 0 in the low and the 0 in the high. Are you with me? So do you see what this AND Z circuit does? If this AND Z, here let's take a look at what that does. The Z can be set in one of two ways. If the AND Z control signal is 0, Z is set directly from the ALU Z out. But if the AND Z control signal is 1, then Z is set as the AND of the ALU Z out and Z. Now, does that make sense? Well, I really wanted to, so here's the truth table. Here's the truth table of the Z out, of what that AND Z circuit has to do. Let's count inputs and outputs. Here, let's take a look at this AND Z circuit. How many inputs does it have? 3. And how many outputs? So it's a 3 input, 1 output. Are you with me? And let's see if this truth table makes sense. If AND Z is 0, which is the first 4 rows, then what comes out?
Z out.
The same as Z out. Are you with me? 0, 1, 0, 1, 0, 1, 0, 1. On the other hand, if the AND Z is 1, what comes out? The AND of Z and Z out. So that's a simple, yeah. Are you with me? So you could design that. In fact, you probably will. I think I probably assigned that homework assignment. All right? Now, I really wanted to do a demo. I was ready to do a demo today. But today, we'll call it quits for today. And because what we've done is we've gone through a kind of an exhausting description, maybe, of what this does. And tomorrow, there's a really slick, you know how we had, you know how you guys used PEP 8 with this assembly language and translator, blah, blah, blah. Well, guess what we have? We have a PEP 9 CPU app that's going to actually let us, it's going to simulate this. And we'll see an example. So now tomorrow we'll see how this thing, how to actually set up those control signals and use the app to set the control signals to have the data flow through the data section like we want it to. And then and once we figure out how that works, once we see how that works, then we'll see how the instruction set actually gets executed, how each instruction in the instruction set actually gets executed. And we will have meet. North will have met south. Nice. Huh? Okay, see you tomorrow.